great pleasure to introduce today's speaker, Greg Hager, who's a faculty at Johns Hopkins University. Greg is one of the most famous roboticists out there. He received many awards for his work and also plays many national, international leadership roles in our community. Greg is one of the few roboticists, I think, that are equally at home in robotics and computer vision. So at the time when I, for example, was still trying to figure out how to use sonar sensors so that our robots wouldn't crash into walls, at the time, Greg was already looking into robot manipulation and vision, and in fact, he wrote one of the seminal papers on visual servo control, which is how we can do closed-loop control with visual data and use this to control manipulators. And if you look at what's going on right now in deep learning, a lot of the work that is using deep learning to learn controllers for certain tasks, they're kind of borrowing many of these ideas where you have a current perception of the robot, for example, or of an object, and you have a target perception, and you try to learn controllers that match these two. And it actually really goes back to some of the seminal work that Greg has done in the past. What I also like about Greg's research is really that it's driven by real-world applications. So he's mostly looking at application domains in industrial robotics and in the medical robotics domain. We're both very interested in this interplay between kind of model-based reasoning and deep learning. In fact, we just are we finishing up, right, a joint NRI project on how robots can learn intuitive physics models. And I think most of the ideas, nice thing is that we had for this proposal, we came up with during a ski trip we did together. And today I'm happy to see him started on the talk on fine-grained manipulation. Welcome.
All right, thanks, Dieter. It's great to be here, particularly on, I guess, a rare sunny day in Seattle in the winter. But what I think is ironic is, if I were to introduce Dieter, I could say almost exactly the same things about him. So I think it's simply a mutual admiration club that you're seeing here. But as the talk title suggests, I'm going to talk a little bit about really a pretty broad spectrum of work that I've been doing in my lab over the last decade or so around fine-grained manipulation. Before I do that, just a quick ad from our sponsor. I just want to say a little bit about Hopkins. I know it's in a city far, far away. So I'm actually coming out of the Laboratory for Computational Sensing and Robotics. It's a collaborative lab that we formed there about a little over 10 years ago now. It actually grew out of an NSF Engineering Research Center on computer integrated surgical systems that we used as a kernel, and we expanded it out. But you can see I think it's, if you look across the country, it's one of the robotics labs that's probably the most collaborative, I think, that you'll find. So Dieter mentioned this interplay between computer vision and robotics. At Hopkins, we have a joint facility, and we put everybody in together. So if you go and you talk to a student, you don't know if they're a robotics student, a computer vision student, a mechanical engineering student, control, or computer vision. And that really has been our vision for robotics. And I think that's one of the neat things about robotics as a field is it has so many facets, but yes, it connects so centrally in so many ways. So I put this up. If any of you happen to be looking for a place to do a PhD, or you've done your PhD and you're looking for a faculty position, I would love to hear from you, because we are, like everybody else, really looking to expand our footprint. My lab, which has been at Hopkins now for about 20 years, I really started to think already 20 years ago about the interaction between people and robotics. So I named it Computational Interaction Robotics Lab, because I knew I wanted to do robots, but I really had this vision that someday a lot of what we're going to be thinking about is how people interact with robots, not how you make robots fully autonomous systems. We do a lot of different things, but today I'm going to kind of focus on these three themes. So you can really kind of think of it in one direction as taking data from the world and trying to understand what people are doing in the world. And so I'll talk about some applications in video understanding for complex activities. We have a very deep footprint in medicine. I started working in medicine about 20 years ago in particularly robotic surgery. And there you might be thinking the game is, hey, what we want to do is we want to automate surgery. In fact, maybe that is something we'll be doing in the future. But our first interest was really that robots were data collection devices. For the first time ever, you had a robot, you had it sitting in an operating room, you had a physician connected to it that was doing a procedure, and it was getting stereo video from inside the patient. So you had the opportunity, for the first time ever, really, to make a complete record of what a surgery was. What did the surgeon see? What did the surgeon do? And so you could start to try to understand, well, what's the process that connects, vision, what they're seeing, to what they do. And we've continued to work in that to the point that we really now start talking about ways that we can use data analytics derived from surgery to, in fact, start to understand surgery to the level that we could potentially individualize instruction and support for surgery. And then finally, I am interested in turning this around and going back into the real world. So I don't want to just passively observe. I want to do. So we have some work going on also in manipulation. And of course, these days, that really means machine learning. In fact, I guess all of these days mean machine learning in one form or another. So a lot of what I'll talk about is also how we're trying to navigate this interplay between using data-driven methods, which have had obviously tremendous success, but also contextualizing it within the domain of application that we're trying to work in. To drill down a little bit on that, so what really sets a lot of this work apart, I think, particularly when you think about machine learning, is that more and more we see the world being this kind of end-to-end notion of if I can create a large enough data set and if I can create enough diversity of labels and really input, I can essentially regress from input to output, and I can learn how to do something. And that, of course, makes sense when you've got a task that, in some sense, is well constrained. But if you start to think about the complexity of, for example, an activity like surgery, where you're doing this fine physical interaction with the physical world, imagine that I wanted to learn how to do surgery end to end, right? Do you really think that's possible? I mean, the Da Vinci these days does a little over 1 million procedures a year, so it's a lot of data. But I just don't think I'd really want to have a robot that has just seen end-to-end surgeries operating on me. I think I'd like to have a little bit more insight into that process. And a lot of the complexity there really comes to the fact that you're doing this very fine-grained manipulation, like suturing, on tissues in a very high-value environment, an environment where mistakes matter a lot. This is another activity that...
Totally off the subject question.
Yeah.
Sorry, what's the current data on outcomes from robotic surgery?
So data from outcomes, there's a bunch of studies. What you can probably say is that outcomes from robotic surgery are no worse for patients. You can look at some outcomes and people see a marginal improvement in some ways. You can look at other outcomes and they're pretty much a wash.
But this very expensive device isn't actually helping the surgeon, is that right?
Well, so let's think about that in a different way, though. So there are a couple of things to be aware of there. First, one of the things you're not controlling for there is what surgeries is a surgeon willing to do. So, for example, I might not be willing to do, like if you do laparoscopic prostatectomy, for example, it's a very delicate procedure. People talk about it like peeling an orange. Is every surgeon going to be willing to do that using traditional laparoscopic methods as opposed to open? Maybe not, but with ergonomics, stereo vision, scaling, motion scaling, they might be willing to do it.
Damping of, okay, got it. Okay.
Yeah. So I think it's a bit more nuanced than just saying, are the outcomes better? And part of that, quite honestly, is most surgeons that I work with wouldn't do a surgery if they didn't think they could achieve a good outcome. So I think you have to think of a little bit more in, let's assume outcomes are going to be good. Now, what are the sorts of things that you're willing to do? The other thing I will say is if you want to look at surgery as a field and you look at the injury rate in surgeons, if you're a minimally invasive surgeon, spine, neck, by the time you're in your mid-late 40s, you're often experiencing problems because it's not a very ergonomic procedure. So there's also a question, are you extending the lifetime of a surgeon? So this, let me go back. And by the way, I do welcome questions. So please feel free to interrupt me. In fact, I told Dieter this is an experimental talk. So afterwards, I'll give you a little rating form. You can tell me which parts you liked and didn't like, and I'll swap slides. Here's another project we've been doing. This is some work with cognitive science and education. So we built a little data collection system where you can see we've got a child here who is trying to replicate that little Duplo structure there. And this is actually something that's a fairly standard testing rubric. It actually is used to assess spatial reasoning skills. So children that are able to replicate structures and without making mistakes and doing it quickly and efficiently tend to have higher spatial ability, mathematical reasoning ability. They tend to be kind of more suited for science, other STEM disciplines. And so there's actually a large interest in doing this. Right now, the only way that you can do this is you do it by basically sitting there with a survey and watching them. But we can actually quantify exactly what those kids are doing, and we can actually create, again, a more structured system that allows us to derive information in this somewhat unobtrusive way. But if you think of what we have to do, we have to actually analyze where each of those blocks went in a very exact fashion. So again, I don't think I'm going to train an end-to-end system that's going to tell me from video to what the exact configuration of the blocks are. And then last example, this is some video surveillance. And you can see that, again, we've got a lot going on in this scene. And imagine that I want to essentially allow you an arbitrary query. Like, you tell me if there's a person walking through this parking lot who approaches a white vehicle, sets a package down, and walks away. Again, not something that I think I'm going to do end-to-end training on. So the point of all this is that we're really looking at a set of problems that are very different than what you see in a lot of the computer vision community these days. So if you go to the computer vision community and you look at video, they're looking at, let me take a video clip and let me see if I can classify if it's somebody putting on makeup or somebody skiing or somebody cooking. So you can think of it as, in terms of temporal granularity and spatial granularity, I just want to put a label on something. Now you can imagine exploring other parts of this axis, like you could break down the temporal granularity a bit more. So maybe I want to say not just cooking, but I want to know what are the steps in the procedure. Or maybe I'm doing the analysis and I want to know some more fine-grained kinematics of the person. But really, a lot of the problems that we're interested in are in that upper right corner, right? We're looking at something that's got fine spatial granularity, it's got fine temporal granularity. And again, just in terms of combinatorics, the amount of data and the number of labels you'd have to think about really don't make it a natural candidate for an end-to-end system. And in fact, if you look at it, complexity is going this way. Typically, the amount of data you have goes that way. Most of the tasks I just showed you, I'm not going to get millions and millions of videos that are labeled in a way I can do machine learning. So that's just a long-winded way of saying, there's a whole space of problems that I think right now the field of computer vision isn't really paying a lot of attention to. And I think a lot of those are problems that are, in fact, highly relevant to robotics, because if we want to create systems that are able to go into the real world and do high-value, fine manipulation tasks, we have to understand things at a much finer granularity than just saying, I want to put a label in a video. So what I'm going to do is talk about kind of 3.5 things, I guess. I'm going to talk a little bit about how we are starting to approach fine-grained video analysis. Talk a bit about the idea of using simulation to actually do data augmentation. A little bit of work on learning for vision-based tasks, kind of touching on all those themes that I mentioned earlier. And then depending on time, I'll talk a little bit about, well, it's great that we can do all these things in the lab, but what would it take to actually move it out into the real world? And if I know how my talks usually go, I'll get to about 2.5 of those, and then at some point I'll jump to the chase. So let me first talk about video surveillance, because that's where all this began. So we actually looked at a problem. This is a problem that was put out by IARPA at some point. It's called the DIVA project. Their problem is we've got millions of video cameras looking at a scene. Let's say it's Boston, and a marathon is running, and all of a sudden a bomb goes off. And we would like to very quickly be able to look through that video and find certain types of events that might be suspicious behaviors. And we may even know something already, right? We don't, just saying suspicious behaviors is hard, but we actually know, okay, it's going to be 2 people, one of them's wearing a black leather jacket, they're carrying backpacks. So we'd like to make a query and just say, hey, could you find this? So if you think about a query like that, the thing that we observed is that most of these queries break down in a very natural compositional fashion. We can talk about actors, we can talk about what the actors are doing, we can talk about what they're carrying, we can talk about how those things change over time. And so we approach this very much as a compositional system. Let's take that query, let's break it down to its components, and let's think about doing the analysis in terms of the components and putting it back together. At the same time, what's kind of neat about this, and this gets to simulation, is once I've done that, I can think of that as a method for analysis, but I can also think of that as a method for synthesis. If I know the actor, I know what they're doing, I know what they're interacting with, I know some of the attributes, I could generate synthetic data that would actually simulate what that activity would look like. And so our goal was to really explore this synergy between being able to generate, if you will, data that's representative of a task, and also at the same time compose some type of system that's able to do the analysis in terms of those components. So this is just an example. So one of the highly descriptive terms they have is entering. Well, what is entering? It really means a person comes, they open up some sort of a door, they disappear inside of whatever it is, the door they've opened up, and then they disappear from view. Now the key thing to know about this project is they want you to be able to do this in a very generic way. So for example, maybe my data set has cars, and I've seen people enter a car, but then in a hidden data set, maybe I don't have cars, I have a building. And I want to be able to detect the same activity, but now it's happening with a building. So something the system has never seen before. But I would know that a building has doors just like a car. So there should be the possibility of just kind of changing that one object, and I can still represent it. So this is a sort of video that they give us. And actually, this is kind of showing how this sort of analysis goes. So here's a car. You can see it was moving. It's come to a stop. And all of a sudden, at some point, kaboom, we see a person has appeared. And that person is now near the car. But eventually, they're moving away from the car. And there's another car showing up. So I showed this trace for this car and that person, but obviously at this point there'd be a new trace. So there's this ticker tape of just different events that are happening all over the place. And really our job is to go through all this and say, hey, this correlation of activities corresponds to the thing that we happen to be looking for. So we actually have developed a system that does this. In fact, I'm going to show it not just in surveillance, but in a few different domains. So for the purposes of what we're doing, think of the problem this way. So I've got some activity like surgery that I decompose into some actions. And the actions are what we care about. So an action is like pushing needle through tissue or throwing a javelin. And the key thing is we're going to assume that there are a set of attributes that are related to that activity. So attributes are things like the objects that are present, proximity, the types of movements that are taking place. Think of it as a basic language of description. And the goal is quite simple. Given a particular query, we break that down compositionally into a set of attributes, so a descriptive language. And then given that description, what we want to do is we want to look at the video and we want to find that activity again. So you can really just think of it as a matching problem at that level that says, look, I've got some action, I've got some set of attributes that describe it. And I've got some video, I've got some attributes that I've extracted, and I want to find the places where somehow between these two there's a good match, and that's going to be a potential source for the answer to my question. Again, the key point being that exactly how I put these attributes for a particular activity together could be something that's totally on the fly. I may never have seen that particular collection of attributes before. Now, people have thought about attribute-based approaches. Interestingly, they think about it mostly in the terms of static images. And in fact, there is a data set. This is the Olympics data set. I can't remember if it has a number on it. But what they do is they have a set of Olympic sports, and they've actually created a standard set of attributes for this particular set of activities. You can see indoors involve waters. They have a big ball. One arm open is a body posture. Throwaway is obviously an action. One arm swing. So there's a language of attributes they've defined for us. And of course, in computer vision, this means now we've got a benchmark. And once we've got a benchmark, we can generate lots of papers about this problem. But interestingly, everybody does this statically. So they try to come up with an attribute language that lets you statically classify a video. So you extract them, you just say, OK, were the right attributes together? But if you think about throwing a bowling ball, well, yes, it's indoor. There's no water. There's a big ball. But your arm goes throwing, so you go one arm open, no to yes, a throwaway goes from no to yes, a one-arm swing goes from no to yes. So there's dynamics that we want to capture. And so we did the really simple thing. We just said, why don't we capture those dynamics? And let's do it in the simplest possible way. I'm just going to define a finite state system that just describes how these attributes evolve. Now remember, we have no training data for these activities, so the best we can do is describe them. We can't learn in LSTM, we can't learn in HMM. So here we are, we've got a finite state system, and we do things like this. So we can say something isn't there, we can say something is there, we can say things change. So for example, a person disappears, we can say something appears again. All really simple things, simplest things you can imagine. And then we can put them together into a time sequence. So for example, if we take a throwaway, we can say, hey, you know, it started with a ball, we were holding on to it, and eventually we threw it away. So there it suddenly goes, boom. So we actually see this sort of temporal behavior that we're expecting. And so what we can do is we can do you know, a very simple approach. Let's just correlate it. Let's just say, does this time temporal series correlate with what we expect to see for that activity? So you can actually see throwaway happens to have a rule 3, which for bowling, which says, hey, at the end of the activity, they're going to throw the ball away. And, you know, we can do this, what have we got here, at the end. So we say it happens at the end. And so there's our score for throwaway. We can do the same thing for indoor. Well, it's indoor the whole time, so that's a static attribute. And we can go through this, and we can basically do all these activities, but we basically just make a big table. We just describe all of them and say, hey, what happens in it? And this is current state-of-the-art results. So this is, as I said, it's the Olympic sports data set. There is a standard evaluation rubric for this, standard evaluation data, like everything else. The best results before we did this, you can see this is zero-shot learning, so you've never seen the activity before. You're just going to try to detect it. 60%. You can see just doing something really simple like this, already a 10% improvement. And actually, there's inductive or transductive, just has to do with how you do the learning process, but you can see in both cases we get a pretty significant performance boost. So really simple ideas, but what's nice about it is we've actually defined a language of discourse now, and we can actually define anything we want in that language of discourse. We're not now constrained to just this particular set of activities. Here's another example. Here's our DIVA. You saw entering and exiting. So in DIVA, what do? What they gave us is they gave us a set of scenes. This is actually the phase 1 of DIVA. So there's 5 different scenes where we've got lots of video data, and we've got lots of different activities we're supposed to find. So entering, exiting, carrying, heavy carry, pulling, so on and so forth. A list of, I think we had 17 at this phase that we're trying to detect in this entire image. So we have to both localize it and we have to temporally say where this activity is happening. They gave us a training set and a validation set. They had hidden test data that we don't get to see, and we get scored on it. So when we started out, like I think all the teams, we were doing end-to-end training on this. The problem was we don't have enough training data. We've got some tasks, we've got like 6 examples of this particular task. So we would go through and we would try to train, we get some results, we'd upload it, we get worse results because they're giving us videos we've never seen before. We finally said, you know what we're going to do is we're going to train our attribute language on one set, we're going to do our validation on a second set, and just for the heck of it, we're going to create our own held-out test set. But that held-out test set's going to be a scene we never saw before, because that was clearly what's killing us, is they've got videos up there of scenes that have never been in this data set. So any machine learning algorithm has never seen a camera angle like that, it's never seen cars like that, never seen people like that. And again, we got some really nice results on this. So LOSO means leave one scene out. This column is if we train, in this case happens to be a TRN, on the videos, and then we test on the left out scene. And you can see the results are actually pretty abysmal. And in fact, if we use this sort of attribute language, we get a factor of 2 performance improvement on this. And this kind of makes sense, because if you think about it, if you're training end-to-end on the scenes, you depend on everything in that scene, the buildings that are in the scene, the sunlight that's in the scene, the camera angle that's in the scene. If what you're trying to do is you're trying to detect people, cars, certain types of objects. You've probably seen those people, cars, and certain types of objects in some form that's very similar to what's in this held out data that you've never seen before. And so the attribute detectors actually maintain their performance almost undisturbed on this held out scene, whereas the machine learning algorithms that are doing end-to-end just fall off the cliff. So this gives us tremendous robustness. It also is kind of neat because our attributes, we actually did no work to get our attributes. We did off-the-shelf person detector, an off-the-shelf car detector, off-the-shelf object detector. So we did actually no machine learning. Like we just, we're consumers as opposed to producers of machine learning models at this point. And it gave us this sort of performance improvement.
So when you get this training data, are you using it to maybe refine the attributes, or are you learning the state transitions of your...
Actually, this one, I should say, there's two versions of this, and now I'm trying to remember. This is the off-the-shelf one. So, no, actually, here's what's going on. So the training data we're using for the TRN. So we're benchmarking against a machine learning algorithm here. So we're using those two data sets for the TRN training. But we actually don't use it for our training because we just pull things off the shelf. And by the way, we played with fine-tuning and some other stuff. Like this is all a leaderboard. So in some sense, the program continuing depends on leaderboard progress, which incentivizes everybody to find some way to get a better number. So anytime we fine-tuned, we could make our numbers better on the scene data and plummeted on the held-out data. So we were just, any data that we had was not enough. We simply were overtraining. And this is the only thing we found that actually maintained our performance consistently across the board. And again, it's, we can define activities that they haven't defined. Like we can actually go and say, hey, can you tell me about 2 people loitering next to a car for a certain amount of time? And that's a perfectly fine query. We can do that even though it's not in the language. There are a couple other...
Exiting is easier than entering.
Why is exiting so... I think it's a little bit of an artifact of just how we do the parsing. So exiting, the person comes out, we have pretty good detection rates as soon as the person comes out and starts to walk away, and the system picks it up. And in entering, there are a few cases that for some reason, it just timing-wise, it doesn't quite detect the person disappearing at the right time or something like that. It's some artifact like that. I don't remember off the top of my head, but we went through the same thing. I mean, imagine an hour-long meeting of trying to figure out why entering and exiting. But one of the other things about it, just kind of to that point, is you actually can do that sort of diagnosis because now that you've got this kind of more fundamental language, you can say, hey, we're not doing great on exiting, or we're not doing great in entering. Let's look at it. We do have some ground truth. Let's run the attributes for the ground truth against what we discovered. And is it a failure of attribute detection, or is it a failure of the rule itself, or is it an outlier case that requires some embroidery? This is actually a case that we did. So there was an action pull and an action heavy carry, and for a while we were confusing the two. This is flipped. This is not accuracy. This is a different metric. So lower is better. We were confusing the two because we basically said, well, pulling and heavy carry both involve the proximity of a person and an object that continues over time. But what we didn't say is, well, when you pull something, it's on the ground, and when you do heavy carry, it's up on the body. All we had to do was to add an extra constraint, and suddenly our numbers went way up. So it has, I guess as a computer scientist, it feels a little more like debugging something that I understand, because I can do an analysis, say, here's what's wrong, and here's how I fix it. So it's very interpretable and explicit. Here is kind of the flip side of that. So this is a case where just our human detector failed. So there is a person, there's their head right there, but not surprisingly, our off-the-shelf human detector just didn't find a person there, and so it failed to detect. So here we would probably go back and we would probably either embroider on our human detector somehow or come up with some other information channel to make use of. So, yeah.
Not a stupid question. I'm interested in human performance on these sorts of things. So, for example, I often get one of these tests that says, identify the
Yeah.
pictures that have a stoplight in
And
it,
it
or a
drives you
bridge or
absolutely
something.
insane.
Yeah, and it's unbelievably difficult. There's a huge amount of ambiguity.
Mm-hmm. So it's highly variable. One of the problems we had with the data set is actually it's highly variable, because what they did is they outsourced this is all human annotated data, the training data we had. By the way, in phase 2, they refused to give us any annotations anymore. They said they were too expensive. So it cost them, I think, roughly $10 an activity or something like that. It's crazy expensive to get it right. But so we had some, I actually have kind of a funny set of slides of different misannotations that people did, just like crazy things. But at the same time, there is an activity where it says there is a car turning right, and there's no car you can see in the scene. It's like, where's a car turning right? We thought it was a mistake. And then if you look between two buildings, there is an intersection, and there's a little flip of a car that goes around a corner, and some annotator found it. So that's actually another challenge we have, is people are variable. So that
Constantly failing these tests and having to do a new one. Do it again. Yeah.
I trained machine learning algorithms to fix them. I talked about surgery earlier. Just let's say, could we apply this to surgery? One of the things that we've been very interested in for many years is this is actually the trace of Da Vinci doing a 4th row suture. You can actually see 1, 2, 3, 4. And the colors are different gestures that are involved in it. And so we can do end-to-end training. We've done many approaches to end-to-end training of this to basically get a functional description of what the surgeon did. And we use this, for example, for skill analysis. So this is what an expert looks like. This is what somebody who's never used the robot before looks like when they're trying to do this task. So you can see there's a pretty strong signal there, which is why we would like to extract this information. So we tried this in surgery as well, because it's same sort of fine-grained manipulation activity. You've got needles, you've got manipulators, you've got tissue. And in fact, in 2006, I had a grad student who did the very first work on this, who was trying to train HMMs to recognize gestures in surgery. And at some point, he got frustrated, and he just went through and he literally annotated pretty much the same things that we're describing here. What's touching what? I think it was really just what touching what in the video, and he could get like over 90% recognition accuracy. So we know that that's actually what we need to do. So suffice to say, this is a little more difficult because we're not doing recognition, detection anymore, or just an activity. We're actually segmenting. We're going to segment the surgery into pieces. So we actually basically do Viterbi decoding on our attributes. And we don't get so this is state-of-the-art with machine learning, 83.1. You can see we're significantly below it, but I'll just say up to about here, this was about 2017. So we're actually doing better than 2 years ago, just kind of with some fairly straightforward off-the-shelf training to detect needles, manipulators, tissue, and sutures. And in fact, our edit distance is one of the best that's out there, meaning we're actually getting the sequence almost much better than most other systems. Should you care, you could train an LSTM on this. You could say I pull out the attributes, and then I do machine learning on the attributes. That gives you about 76.5%. So you lose about 5% if you don't learn your own features. You lose about another 15% if you don't actually learn the time series analysis on top of the attributes. But again, promising. I mean, we have, I think, 8 gestures, 9 gestures, so well above chance on this. I threw this in because I know Dieter's interested in simulation. And as I said, simulation is a piece of this. So one of the things that would make this even better would be if when somebody puts in a query, we could actually use simulators to bootstrap that query, because we don't know a priori that we have all of the attributes we need to detect something. So we've actually developed a simulator for DIVA. So you can see here we've got cars, we've got people walking around. You can see it's not great graphics. There's a guy that seems to have gotten stuck between a car, but he's still walking. But not the sort of thing that we've focused on at this point. But what it lets us do is get a huge variety of data and actually start to explore, can we augment our real data with simulated data? We had some past experience with this. This is a 2018 PAMI paper where we actually were looking just at car detection. We used a simulation to generate car data. We trained a deep net from that data, but we tapped into the simulation to get a lot of intermediate information that you wouldn't have normally in the real world to train it. And we actually showed that we could do very good car detection, in fact, state-of-the-art car detection, never having seen a car. We just trained it in simulation. We just deployed it in the real world. So this is actually where we thought, we're going to go to town with this. We're going to really solve DIVA with simulated data. Turns out it's not as easy as that. In many cases, we're not able to get that transfer to happen. But what we actually have started to do is we've started to come up with lots of ways to generate good simulating data and then put that simulated data into the system. So this happens to be a case where somebody is doing, you can see some sort of a driving operation. It's a video where we can do very good recovery, so we can get very accurate ground truth. We've actually done whole scene analysis to add ground plane constraints and everything. So we get pretty good simulation of what's going on, and then we can go and we can put it in an entirely different environment in the simulation. So it lets us take real behaviors, which are kind of hard to simulate ab initio, and transfer them into a whole different set of scenes, and then use that simulated data to go back and augment what we had before. So we've looked at different ways to leverage this data. As I said before, you would like to think that you can just take simulated data, you could feed it into the system, it would learn something, and then you could deploy that in the real world and it would work. And absent magic at NVIDIA that I know Dieter's working on, it doesn't work in the real world for the most part. And so what we've started to focus on is, can we leverage a small amount of real data with simulated data? So we give it the true experience of real data, but we're going to give it variety through the simulation. And the way we do that is two ways. We either fine-tune, we train in simulation, and then we fine-tune in real data. So think of generating a huge amount of simulated data. You've got a model. You have a little bit of real data. You fine-tune at the end, and you run. Or we do adversarial methods. So the other way you can think of this is, I'm going to put in both real and synthetic data, but I'm going to add an adversarial loss term that says, I don't want to produce features where I can discriminate the simulated data from the real data. And so I have to develop features that are common to both as opposed to somehow unique. And what I'm trying to do is trying to constrain the information channel and just say, look, I want to find out things that are about the actions that I'm trying to represent as opposed to about a simulation or the real world. And this is the sort of results we've had. So this is sim to real ratio. And what you can think of here is, I'm taking a fixed amount of real data and I'm slimming it down. So I've got a certain amount of simulated data, and I can now look and say, well, given a particular ratio, how well do I do? Well, if I only have 1/32 of the real data, I really do abysmally badly. This happens to be on the National Taiwan University activity data set. So I do abysmal if I just train on the real data, but if I add the simulated data, I'm actually doing pretty close to as well as I do if I use all the real data, plus now I'm down to a factor of 4 more simulation. And so this is where we've actually been able to make hay on simulation is, those labels I mentioned were very expensive. I only need 1/32 as many labels, and I can get very close to the same performance. This is DIVA, and you can see we have less real data, so the ratios are a little bit different. But nonetheless, you see this kind of consistent performance improvement because I augment the simulated data with the real data. And this is the thing we're actually getting better and better at now, is not learning ab initio from simulation, but leveraging simulation to actually improve performance.
Is that with the GAN setting, or did you use a GAN for that setting?
No GAN.
Just augmented, just added.
So what we do is we simulate, like you saw. We do texture randomization so that there's nothing about the way we render that it can pick up on. And then we either do fine-tuning or we do adversarial. And as you can see, we get about the same performance for both. So whether we do it serially, simulated then real, or whether we do both together. Some cases we see a bigger discrepancy, but for the most part, either one works. But the key thing is we can generate practically infinite amounts of simulated data, and we just kind of see continued performance improvement once we have enough real data to kind of pin the system down a little bit. This is actually, I put this in just because I like watching this. This is the system training. So this is taking the feature space, projecting it, and seeing how the feature space evolves. On the left are the different classes color-coded. On the right, the colors are real versus simulated data. So you can see we have a lot more simulated data than the real red dots. And you can see the classes kind of emerging as it trains. But the key thing is you notice that the simulated data and the real data is all mixed in, right? There's no real discrimination there. If we don't have an adversarial loss, this is what we end up with. So it learns two completely separate paths, one for simulated data, one for real data, and the features are different. And it's no surprise, you know, if you look at a picture like that and you say, okay, now I'm going to train from simulated data and apply to real, why it doesn't generalize. The language it's speaking is just different. And the adversarial loss in particular just drives those two representations together. So we're pretty excited about this, and we're continuing to try to push on it and get some better results. I have like maybe upper bound 7 minutes left. I'll say just a little bit about going from learning to observe, this has all been passive so far, to doing as well. So as I said, ultimately I want to perform fine-grained activity. So we've been playing with this sort of a setup where we just have a bin, we've got some distractors, we've got some blocks, and we're simply trying to teach a robot to manipulate in that environment. And the key thing here is to think about that temporal granularity now. So we're going to do this using reinforcement learning. Reinforcement learning is great when you've got kind of a very fixed goal, and that goal is relatively closely related to the actions that lead up to it. I'm going to try to get this robot to build a stack of 4 blocks. And what it does with the first and second block are not particularly closely related to what it does to the third and fourth block, at least in terms of the reinforcement learning. To get to the fourth block is actually extremely hard for it to do. So there's a lot of shaping that needs to be done to get a system like this to work. And that's what we've been doing is deciding or learning how to create feedback methods in reinforcement learning to make the system be able to do these fine-grained multi-step activities like we've been observing. So, you know, if I were going to write a program, it would look like this. You know, I would just say, find something. This is to do something different. This is actually from a paper long ago. But the analogy is, I'm actually going to essentially embed this sort of a program construct in my reinforcement learning to solve the problem. So just like I said, surgery breaks down into chunks, and activity recognition breaks down into chunks, and my kid block analysis breaks down into chunks. When I want to learn activities, I think I need to do that same breakdown. And so this is a paper we call Good Robot. The idea is how to build a reinforcement learning method that rewards incremental progress to tasks, step-by-step progress, in a way that gets rapid convergence, but at the same time doesn't dig you into a hole. And actually, there's 2 key pieces to it. Part of it is essentially this term, which is an incremental reward term that says as you progress in a task, you get more and more reward. And the other is this term. This is actually, the student Andrew Hunt calls this a spot reward. It actually comes from training pets. So it turns out that there's a pet training method where you're trying to get your pet to do something, and you give them treats if they make positive progress towards what you're trying to train them to do. And if they don't make positive progress, all you do is you withhold the treat, but you don't punish them. You don't say bad dog or anything like that. You withhold the treat. And so that's what this is. It basically says if you progress, you get the treat, you get the reward. And if you don't make positive progress, I'm not going to disreward you, but you get nothing for it. And so that turns out to be one of the key steps to actually getting this to work well. This is actually what the system looks like. So we start out with a bunch of blocks. We get RGB data. We've trained through reinforcement learning, a neural network that looks at the blocks, and it basically gives us Q scores, quality scores for 3 actions, push, grabs, and place. But what you see is those scores are distributed across the image. So you can think of the colors as basically, you know, for example, saying, well, this is a great object to grasp right now because it happens to be aligned with the gripper. This would be a great object to place on because it happens to be already on a stack. And so then it's just doing typical Q learning. So we learn this function from data and experience, and we choose the action that's the highest quality action. The kind of funny rotations here are that we basically discretize the space and we discretize rotations. So we're really just learning this activity map over all of those. So we've done this in simulation, and you can show that this sort of spot reward function does actually better than state-of-the-art by a pretty significant amount, 5% to 74%. On these sorts of multi-step tasks, we do both stacking and row making. So all this in simulation. One of the things I want you to notice is that number, 35,000. So 35,000 is the number of iterations, learning iterations, that we had to perform to get it to learn. So I'll show you in a second. In fact, I have it in a second. But imagine that it takes about 30 seconds for the robot to do something in the real world. I can't do the math off the top of my head, and I didn't do it before this, but I know what 35,000 times 30 seconds is. I don't think it's the lifetime of grad student, though, or within the lifetime of grad student. So this is great in simulation, and it showed us that this works. So what we've been focused on is making it work in the real world. So this is the same system, but now for real-world blocks. And the one thing I want to point out here is we had to get that 35,000 down. Well, I was talking with Dieter about this beforehand. What we did before is kind of a classic reinforcement learning thing. Let me just assume I know nothing. I'm going to give you rewards, and eventually you explore the action space and you learn a policy. That's great. It's kind of fun. And if you Google, you buy a bunch of robots and you let them work for I don't know how long until you learn something. But the fact is, kind of like that program I showed you at the beginning, which gives me some of the temporal sequencing of the activity, I know a lot of heuristics about what's going to make this thing work. For example, if I want to manipulate a block, searching for actions that are heading away from the block aren't going to do anything for me, right? It's just a dumb thing to do. It's a part of the search space that has no information in it. So we added a few things, like we add some masks that simply say, here are blocks, here are areas around blocks. And we basically use those masks as extra hints to the algorithm to say, look, you can use this information to help drive the search. So that plus a few other improvements to the algorithm, and we actually are starting to see the robot learn in the real world. This is hot off the press, as in, what is today? Today's Friday. This is probably Tuesday. So it's getting better. It's probably better today. But the key thing I want you to notice is this. Number of actions is 1,000. So I had 35,000 iterations before, and we're down to now 1,000 actions with the robot. You just saw an action up there. It maybe is 20 or 30 seconds, but I can live with something that's 1,000 30-second actions. It's doable in a day's time as opposed to a week's time. And just to kind of give you a sense of what it looks like, this is a robot learning stack, sped up a little bit. So this is early in training. You can see it's kind of moving blocks around, but every now and then it gets a stack, and that little reward function fires, and it gets a little happier. And then after we train for a few more hours, you notice that the block stacks are getting higher. We're seeing stacks of 3, and we're seeing stacks of 4. And it's kind of steadily getting better and better and better at doing our stacking tasks. I don't ever expect it to asymptote at 100% because we're doing machine learning, and nothing in machine learning ever asymptotes at 100%. But it's actually, let's just say the grad student who was doing this got very happy when he started to see this happen 2 weeks before the IROS deadline. So we're obviously continuing to work. Robot's better today than it was when I put these slides.
Very good. Do you know how much of the data you throw away kind of through this notion of stuff that didn't really work out, that you're not even using this in your Q function updates? So you're kind of throwing that data away, right? Do you know
the masking? The masking you're referring to?
I think the idea with the spot where you say you're not
sure.
giving the reward, you're not using the reward at all.
Yeah. I mean, I couldn't really tell you at this point how much we throw away. I can tell you if we don't do that, learning basically doesn't happen. Like that turned out to be one of the key pieces of this is what it would do, for example, is it would decide to take a block from the top of the stack and take it off. And then it would take that block and put it back on. And it could sit there like essentially harvesting rewards by just taking the block off and then putting it back and taking it off and putting it back. So it kept giving a positive reward every time you put a block back. And that's what it does, is it kind of gets it out of these cyclic loops. Yeah?
So this spot reward has this weird solution that if you create these towers of 2 cubes and then topple them over and then put them back, you constantly get like reward whenever you put the second cube on top of it. So what makes it to make a tall tower?
Well, actually, that's what it avoids. That's what I was just saying is before it actually, that was actually, well, actually, right. So if we penalized it for that, then the problem we got into is it just wouldn't converge. Like it would never do things, because anytime it made a mistake, it was bad. And so it actually kind of just moved blocks around, but never actually commit to building a tower.
But could it still have this solution that it constantly drops it and then puts it back up and then constantly gets reward?
Well, but except the reward goes to, it gets 0 reward if it topples it over, right? And then even if it builds, let's say it topples it over, let's suppose it had a stack of 3 and it toppled it over. If it builds a stack of 2, it's still getting 0 reward because it hasn't progressed beyond its previous high point. So it has to actually keep progressing. And that's exactly what we're trying to avoid, is this. I can get rewards by just kind of playing with my blocks but never actually getting to the end of the task. Because, I mean, these things just have so many local minima. It's just crazy.
So when does an episode end in this setting then?
An episode ends when it either has 4 blocks stacked, or there's an upper bound. Like at some point we just cut it off and say, okay, you failed. And so it has, I mean, we know something about action efficiency, so we know if it hasn't done it in a certain number of actions, we can just pull the plug and do it again. All right, I'm going to cut to the chase. I could talk about surgery and talk about machine learning and surgery, but I think I'm going to skip that. I told you this would happen, and I'm not going to talk about some stuff we're doing in unsupervised learning. I'll just maybe say one last word about this. So, as we've gotten more and more into the machine learning world, and I'm doing work in medicine, I actually have a company that does manufacturing that's starting to do machine learning work. One of the things I've started to think more and more about is how do we actually verify the quality of performance of algorithms of this type? And we've seen this in automated driving as well. So this is actually kind of an idea that Vijay Kumar and I were kicking around for a while, which is to try to figure out how do we actually put some sort of a structure on machine learning type systems and their level of ability. And the starting point of this was that in automated driving, they talk about autonomy levels. And they talk about, well, you're going to get to AL1s, or 0, 1, 2, 3, 4, 5. But what they don't talk about is the environment that you're actually trying to do it in, and how hard it is to, for example, do fully autonomous lane following in a well-lit situation where the roads are well marked versus in Nairobi somewhere where you're on a dirt road that has no lane markings whatsoever. And so I started to think with some of my students about how do we actually put some sort of milestones and benchmarks. This happens to be in surgery, where we think about the complexity of the world that we're dealing with as well as the level of autonomy we're providing in it. So for example, orthopedics in surgery is relatively straightforward because it's all rigid objects, whereas HIPEC is a procedure I won't even describe to you because it's frankly just a little bit disturbing. But it's a very difficult procedure to do, something we're not going to do autonomously for a long time. And the real question is, of course, how do we kind of populate the world with things that we are trying to do? And in particular, kind of back to this question of end-to-end training. We're never going to get there with just data. Data is necessary, but understanding the structure of tasks and understanding what the failure modes are in those tasks is going to be one of the key things that we're going to need to figure out for these machine learning algorithms. And we started to do this. I won't say anything about it because, again, I want to just end. But I'll just say, so this is kind of a tour of what's going on in my lab right now. And as I said, we're really trying to explore this space of how do we take advantage of machine learning in every way possible. It's just incredible the sorts of things that we can do today that we couldn't do 5 years ago. But at the same time, wrap it into a context where we're taking advantage of what we know about a domain. So in surgery, I know a lot about what's going on in in that surveillance setting, in the kids blocks world, there's a lot of domain knowledge that's there that if you can wrap it and build it in a kind of structured and generalizable way, you can make way more progress than if we just keep thinking about how can we do the next best end-to-end machine learning algorithm. Even though I know from a grad student point of view, there's no more fun than setting your algorithm running, going out for a beer, and coming back the next day and having it do something really cool that nobody saw it do before. But I really do believe that we need to start to invest a little bit more in structured engineering of these systems to make progress. So let me stop there because I know I've kind of worn out my welcome at this point. Thank you very much.
Any questions?
Yeah.
So about your work on activity recognition with applications, so you talked about end-to-end mapping. So palatable, and I'm curious about your view on, so there's a lot of interest in the intersection of natural language and computer vision, so you can imagine watching a lot of movies, Netflix with subtitles, so annotation, somehow learning, through the compositional nature of the language.
Exactly, yep, that's kind of where we started.
Never seen it before.
Yeah, so I totally am with you. That's actually where I would like to see this go. In fact, we have a robotics version of that project where that's actually the idea that you give the robot a command and it essentially composes on the fly to perform the task. That's actually where some of the reinforcement learning stuff came from. One of the things we're doing there, which I'm really curious to see how it works out, is in medicine. We're doing recordings. In this case, it happens to be colonoscopy. But in colonoscopy, believe it or not, there's a set of strategies you use to do a good job. For example, being able to kind of see around corners and kind of make sure that you've viewed the entire area. When an expert is teaching someone that procedure, they obviously narrate a lot of what they would be doing. And so we've simply asked attending clinicians who are doing a colonoscopy to narrate what's going through their head as they do the procedure. And we're building up this archive of video, again, you probably don't want to see. But it is a procedure that's done fairly often, and their exposition of what's happening, and you start to see a vocabulary emerging. Right, there are repetitive things that they do, and that utterance correlates with emotion in the video that we can actually cross-label and start to say, well, the grounding for this is that, and then we can start to think of, for example, a novice doing it. We can actually detect, did they or did not they not do that particular maneuver in this case. And if they did it, we can say, good, you did that maneuver. And if they didn't, we can say, have you thought about doing X maneuver, where basically it's what the mentor would have said at that point in time. So I'm super excited. I think machine learning, I've said to a couple of people today, has kind of created a francolingua between robotics, computer vision, and speech and language that just didn't exist 10 years ago, and I think the opportunities to kind of cross-fertilize are just huge.
So in the surgery domain, of course, what's really interesting also from a modeling perspective is you have in the suturing tasks and things like that, you have all these deformable surfaces that you have to deal with. Is that an area where you feel like it's better to come up with explicit deformable models for these, or maybe more end-to-end style, almost policy learning, if you have enough data to train systems?
That's what we're actually testing. So the surgery stuff that I didn't show, the goal is actually to do full suture throws where you've got one movement, which is just open space placement. That's not so hard. Drive the needle through tissue and then retrieve the needle from the tissue. And our hypothesis is that reinforcement learning, given in the simulator, you actually get a score for how cleanly you drive the needle. Like if you add force to the tissue or something, you get demerits. The idea is to say this is almost like an Atari game. Let's teach you how to do this, and then to actually start to look at the transfer into the real world. So if we have it do a needle drive, does the reinforced learning version actually generalize? I mean, obviously, if we had a model and we could condition on that model, that would give us better generalization, presumably, presuming we could do model identification. But I think for a lot of what surgeons do, it's pretty much by rote. I think once they know the context they're doing it in, I think it's a learned behavior, and I think we could probably learn it as well. But it's all contextualized, right? So it's for that particular suturing task in that location. If I'm going from suturing in the retina of the eye to suturing in the ball, I don't think it's going to generalize.
All right.
All right, thank you.